Peak Chemisters, this is Mrs. Vanderlei bringing you Blankwalle 5.6 Part 2. So section 5.6 is all about Dalton's law of partial pressure. We learned how that the total pressure is the sum of all the partial pressures of the gases that are present. We learned, let me flip back to the prior page. We learned that pressure and moles are directly related, and we came up with these relationships right here. And we learned a new term called chi. Chi is a mole fraction. What is a mole fraction? Mole fraction is the number of moles of your interested, gas over the total number of moles present. And we manipulated this equation to come up with this. This is the partial pressure of the gas is equal to its mole fraction times the total pressure. So we're going to use this whole idea in number 23. So let's go back to number 23. So it says the partial pressure of oxygen gas was observed to be 156 torr in air with a total atmospheric pressure of 743. Calculate the mole fraction. All right, let's do that. So I want the mole fraction. So the mole fraction by itself is equal to the pressure of the gas you're looking at over the total pressure. So what is the partial pressure of oxygen? It is 156 torr, and the total pressure is 742 torr. And if you divide them out, you get about 0.21. And if you want, you can make that into percentage, and that makes it 21%, and that's really about the percentage of oxygen in our air. I told before that nitrogen gas is about 75%, oxygen's about 21%, the remaining 4% is all the other things, carbon dioxide, argon, that kind of stuff. So yeah, that can again make sense for what we know. Let's look down at problem number 24. Here we have an equation, mixture gases containing 0.2 mole of sulfur dioxide, 0.2 mole of oxygen, and a 4-liter flask to form sulfur trioxide. The temperature is 25 degrees C. What's the pressure in the flask after the reaction is complete? So I'm looking at moles. I'm looking at a reaction. I'm looking at maybe a limiting reactant. So I'm really looking at making a BCA table. So let's see what that's going to do for me. I start off with 2 moles, of sulfur dioxide and oxygen. I start with no moles of sulfur trioxide. So which one do you think is limiting? Go ahead and kind of figure that one out. If you said sulfur dioxide was limiting, you were right. And when we're done, this is what we get. So I need to know what the total pressure in the flask is. Okay, I need to know what the total number of moles are in the flask. So if I use, in a sense, Dalton's law of partial pressure, I can figure out the total number of moles left into my system. And the total number of moles is 0.30. So I have no moles of SO2 left. I have 0.10 moles of oxygen. I have 0.20 moles of sulfur trioxide. I add those all together, so the total number of moles is 0.30. So now I can look over here and figure out, okay, so what is the pressure? Well, PV equals nRT, so I'm looking at nRT divided by V. And if I look, which one it would give me? Well, it looks like either it's going to be or E, because I have a 0.3 here and a 0.3 here. So what's really the biggest difference is this is 298 and that's 25. Well, D and E are really wrong because I didn't convert it into Kelvin. So my answer is letter B. Okay. Number 25, oh, look what I have done. I put a 2-star problem next to number 25. Maybe you should look this over a little bit, especially before your Chapter 5 test. What do you think? So it says, using the information provided in the diagram below, determine the partial pressure of helium and argon after mixing and the total pressure in the flasks. So what's going on? This has a closed stop valve there. And in this left side, I just have helium. Notice it's a bigger container, has 3 liters, and the pressure is 120. This is a smaller container, has only 1 liter and 80 torr of argon. So what happens? I open it up. What's changing? The pressure's changing. Well, duh, it kind of tells me so. Determine the after the effect. But what else is changing? Isn't the volume changing? Yeah, because right now the helium is confined to 3 liters. When I open up the stopcock, I have now a total of 4 liters. Here, I start off with 1 liter, and I open it up, and I have 4 liters again. So both the pressure and the volume are changing. So what does that bring to mind? Boyle's law. Ooh, all right, let's check this out. So for helium, what's my initial pressure? Looks like 120. What's my initial volume? Looks like 3. What's my final pressure? I don't know. That's what you're solving for. What's my final volume? It's opened up for the whole thing, isn't it? It's 4. So if you do your math, you get 20. Does it make sense that the pressure goes down? I hope so. Why? Because the volume went up. So what about argon? What's my initial pressure is 80 torr. My initial volume is 1 liter. What is my P2? I don't know. That's what you're looking for. What is my V2? It's opened up. I have a whole 4 liters now to play with, don't I? And then when I solve for it, you could probably do this math in your head, you end up with 20. So those are the partial pressures of helium and argon. I'm not done yet. What else do they want? They want to know what the total pressure is. So I'm going to add those two together, and I get a total pressure of 110 torr. Okay, so hopefully that makes sense to you. I bet you'll see it again. Okay, so this next section is super duper important. If you're going to collect gases over water, okay, and if you look at this diagram, this is fairly typical of how you collect gases. So what happens here when the desired product of a chemical reaction is a gas, the gas is often collected by the displacement of water as shown as, right here. So here's your reaction. The gas goes through here underwater and it displaces here. So here you're collecting the hydrogen gas, okay? A lot of times this would be a graduated cylinder so you can read the volume of your collected gas, okay? But what is in this pocket right here? Is it just the hydrogen gas? No, what else is happening? What can happen at the surface where the water was? Can some of that water also become a gas? And the answer is yes. So this collection area, it says, is not pure. It contains water vapor and the desired gas. Now think about this. What does the amount of water vapor depend on? Well, when are you most likely to get a humid day? When it's cold and humid? Of course not, silly. It's when it's hot and humid. So the amount of humidity, the amount of water vapor in the air depends on temperature. So as temperature goes up, the vapor pressure of water goes up. And so what do you notice down below? There's a chart here, isn't there? I believe, if I'm not mistaken, there is also a chart on the back of your notes, perhaps, that has a much more extensive one. Now notice the range of the temperature is from 0 to 100. Well, duh, isn't that when water is in liquid form, right? Anything below, ice doesn't really create much of a vapor, and above 100, it's boiling anyway. You're making gases. But isn't this interesting? What is the vapor pressure at 100? Look at that number here, and does that make sense to you? It's 760. Isn't that the pressure of 1 atmosphere? Oh, we're going to come back and kind of talk about that later on, okay? Why is that so significant, okay? So let's look at problem number 26. As a sample of potassium chlorate, it was heated in a test tube. The oxygen produced collected by the displacement at 22, a total pressure. Keyword, a total pressure, because what is in here? You look at the little diagram here. It's not just oxygen, it's oxygen and water, isn't it? The volume of the gas there, the vapor pressure of the water at 22 degrees is 21. Well, obviously this chart only goes by 5, so they had to tell you that. Calculate the partial pressure of oxygen in the gas collected and the mass potassium chlorate in the sample that was decomposed. Well, I think we can find the partial pressure of oxygen pretty quickly. All right, our total was 754. They told you what water was, so if you subtract the two, you now know what the partial pressure of oxygen was. So how are we going to find the mass of potassium chlorate? Well, if I can find the moles of potassium chlorate, can I find the mass of potassium chlorate? And my answer is yes. So I need to know the mass of potassium chlorate. Well, what do you think I can find right now knowing the pressure of oxygen? Do I have the volume? Yes, I do, 0.650 liters. It's right here, isn't it? Do I know the moles? No, I don't. R, yes. T, yes. Can I solve for moles of oxygen? The answer is, well, yes, I can. Okay. And there you go. Here's my moles of oxygen. But that's not what we need. What are we looking for? We're not looking for moles of oxygen. We need moles of potassium chlorate. What are you thinking right now? Are you thinking of stoichiometry? Are you thinking of a BCA table? That's what I'm thinking. Why don't you try this last part on your own? I think you can probably do it. Figure out the moles of potassium chlorate and figure out your grams of potassium chlorate. When you are done, come back. So you better pause this first. All right, this is what I did. So here is my balanced equation. Hopefully you figured that out, okay? So you start with potassium chlorate, you decompose it. You know you're making oxygen. Hopefully you knew you made potassium chloride too. So if you've created 0.02588 moles of oxygen, what's that divided by 3 times 2? I got 0.01725 moles of potassium chlorate multiplied by its molar mass, and there I have the grams of potassium chlorate. Okie dokies, in order to determine the rate of photosynthesis, oxygen gas emitted by aquatic plant is collected over water. That's an important key. Collected over water. Ding, 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 ding. Dalton's law of partial pressure. Whenever you see that, you have to incorporate your water vapor. All right, keep going. At temperature of 293 and a total pressure of 755.2 over a specific time period, total of 1.02 liters of gas is collected. What's the mass of oxygen that is formed? All right, well, what's the first thing you ought to do? Why don't you go ahead and do that? What are you going to do? Did you do something like this? Now, folks, they didn't give you the pressure of water. So at what temperature is this? Well, subtract 273, what do you get? 20 degrees Celsius. Hey, go on the prior page. I'll do it. Ta-da! All right, and now what? Whoops, I want 2 prior pages, didn't I? There we go. And scroll down at 20 degrees, what is the partial pressure? 17.55. What's the unit, by the way? Millimeters of mercury. Oh, I can now plug that in, can't I? So here is our problem. So we got 17.55 millimeters of mercury, right? Oops, sorry. I pulled up the wrong one, didn't I? There we go. So you got a total of 755, my mistake. Is equal to the oxygen plus 17.55, subtract, and that's where you get the 737. You're probably wondering what's going on. All right, so now what? I got pressure, I got volume, I got temperature. Why don't you go ahead and solve for the moles? Go ahead and do this, pause it. Are you back? All right, so I use Pivner, and I'm not going to show you all the work because I think you can probably do it. And I got this for moles, but I'm not done yet. What are you looking for? Grams. Go ahead and do that. All right, oops. This is what I did. I put grams on the top. Oops. There we go, grams on the top, moles on the bottom, and my final answer is 1.32 grams, okay? So that's the end of 5.6. So I'll end as I always do. Don't wait to be great. We'll see you next time. Bye-bye.